Hello, and welcome to this discussion. Today we're going to talk about dimensions and units. So, in heat transfer, we basically have four essential dimensions. Of course, we have mass, length, time, and temperature. So, these are basic concepts of measurement, the thing that we're measuring. Units are the numerical expression of our dimensions. It's based on some reference. For instance, 1 meter is a unit that measures the dimension of length, and it's based on some reference meter that exists somewhere in the world. So what that means is that dimensions are quantified by units. We're going to use SI units throughout this course. So you should be able to convert from English to SI. Now you can see there's a whole bunch of different units here in the table. Length, mass, time, of course, temperature. There's also angles, electric current, amount or moles of a substance. We also have derived units. Things like force, energy, and power, heat, are all derived from the primary units based on their fundamental definitions. Now, in general for this course, it's always best to operate in units of Kelvin or Rankine for temperature. These are called thermodynamic temperature scales, and they're based on absolute zero being the minimum. So throughout this course, you always want to convert temperatures into Celsius or Kelvin, even if they're given in a problem in degrees Celsius, before you do any calculations. Now, there are quite a few key quantities here that we need to keep in mind. The first one is the total thermal energy. It's the energy associated with the microscopic behavior of matter, things like vibrations and oscillations. And that's our internal energy, U, and as units of joules for total or joules per kilogram for the specific internal energy. The temperature then is a means of assessing the total amount of stored energy, but it's indirect. Different materials at the same temperature are going to have different amounts of total thermal energy. So it's indirect, but it's the means by which we generally measure that thermal energy storage. Heat transfer then is the transport of thermal energy due to changes in temperature. So you have to have a temperature difference to have heat transfer, and anytime you have a temperature difference, you will have heat transfer. You also have heat. Heat is the total amount of thermal energy transport. Again, it's in joules, or joules per kilogram on a per mass basis. Heat rate is the thermal energy transport per unit time. Now, heat rate is sometimes referred to as power, or thermal power. Then the linear heat rate is the heat rate per unit length. For nuclear engineering in particular, it's the heat rate per unit length of a nuclear fuel rod. And then heat flux is the heat rate per unit surface area. We also have the volumetric heat rate, which is how much heat is generated in a single unit volume of a particular substance. The next couple pertain directly to nuclear engineering. First is the core power density, which is the total core heat rate divided by the total core volume, not just the fuel, but including the cladding and moderator. And the core specific power is the heat rate divided by the initial volume of fuel, of heavy metal. So the relationship between the heat rate, linear heat rate, heat flux, volumetric heat rate, core power density, and core specific power need to be clearly understood, because the reactor physicist looks at the volumetric heat rate and linear heat rate and so on. Thermal engineers are looking at things like heat flux for looking at temperature changes. And materials engineers are going to look at the core specific power, because they're looking at how much fuel is being used. So different types of engineers are going to use these parameters differently, and we need to know how to exchange information and how to convert from one type to the other. Core power density is an indicator of the size of the reactor pressure vessel, and therefore the capital cost of a reactor per energy produced. And then the core specific power, again, is related to fuel inventory and fuel cycle costs. So they're also of interest to non-engineers who are looking at those kind of cost analyses. Moving on from that, the thermal conductivity is a quantity that measures a material's ability to transfer heat. Higher thermal conductivity means that a material transfers heat through it more easily. The specific heat measures how much energy a material can store if you have a given change in temperature. So 1 degree Kelvin would produce a certain change in energy in the material. The thermal diffusivity is a combination of conductivity, specific heat, and density. It basically measures the ratio between a material's ability to transfer energy and its ability to absorb energy. And then the last one is the convection coefficient, which measures the heat loss from a surface due to convection. We're going to go into more detail about many of these terms as we go through the course. However, at this point, I just want to introduce you to these terms, the symbol we're going to use, and the typical units that that particular quantity is going to have. A word of warning on units: be very careful in how you use them. Make sure your answer has the correct units whenever you solve a problem, and recognize that sometimes units can help you. For instance, if you know the definition of Nusselt number or the definition of the Biot number, and you know what units most of the parameters have, you may be able to work out what units the rest of the parameter, the remaining parameter has. So sometimes units can actually help you figure out how to solve a problem, but you have to be aware of them and you have to be careful.